let me get this going before I forget. All right, so we were talking about chapter 7. Let me share that screen, and we were at slide 17. Let's get to 17. Okay. Now we just begun doing Lewis dot structures for the atoms, and those are straightforward. You simply just find the valence electrons for that particular atom. Keep in mind, we can only do that for those atoms, the main elements. Those are the ones denoted by the Roman numeral and the letter A. So that's groups 1A through 8A. The Roman numeral tells us how many valence electrons they have. So you simply put the symbol, and then a dot represents an electron, and you just put the number of dots around the symbol to represent the number of valence electrons. So when asked me, why do we care about the valence electrons? Because that is where all the chemistry occurs. The innermost, the core electrons, those are the ones inside the valence shell. The valence shell is the outermost shell, okay? And those are full, and nothing's going to happen to them. The reactions occur on the outside shell, and depending on the atom, it will either lose those electrons on the outermost shell, or it will gain them. If it's a metal, automatically they lose electrons. And if they're non-metal, automatically they will gain electrons, okay? All right, so let's continue. So those are some examples of the atoms and the valence electrons, okay, that they have. Now, we're going to start working with actual structures. And so here, we need to make sure that you utilize, as I was stating, let me make sure I have it here. Let me pull it up. As I stated last time, if you've not printed this particular table, make sure you do print it, because we're going to utilize this table to determine the shape of the molecule or the compound that we are going to look at, okay? Because all molecules have a particular molecular geometry, if you will, and they also have a particular name with respect to that geometry. Okay? And this particular table will help us to determine what type of geometry they have. Okay? And it's all related to the valence electrons of all of the atoms that come together to form this compound. And what we need to do is we add up the total number of valence electrons for that chemical, whatever that chemical may be. Now, you will always be told who the central atom is. As I stated before, we're either going to put it in bold with respect to the symbol, or it will be underlined underneath. So it will be the central atom, and then everything else is bonded around it, okay? And if it's bonded around it, it will be either it's a single bond, a double bond, and a triple bond, depending on what the molecule is. Once we count up the valence electrons, we figure out who's bonding around the central atom. We can start making bonds, and we account for all of the bonds and all the valence electrons. And when we do that, after we set that up, we check to make sure that all the atoms have the octet field, okay, fulfilled, except hydrogen. Hydrogen always will have 2 electrons around it. It can't have 8, so only 2 electrons. Now, sometimes this is a bit of a challenge to kind of grasp, because let me cancel that. What I meant to say is this. If I have just a generic formula here, where I have some species A bonded, when again I got a line here, bonded to, say, some other atom, B, okay, very generic. What we have here is a bond. That's what this line represents. And we have 2 electrons in here. There's 2 electrons that are being shared between A and B, okay? Now, those 2 electrons can count both for B and A when we start counting the electrons and making sure that there's 8 around the atoms. So any bond means that whoever's bonded, sharing that bond, those 2 electrons can count to both of those atoms, as when we do the counting to make sure that the octet is fulfilled. You'll see this a little bit clearer as we do some more examples, okay? And remember, hydrogen only has 2. And so an example of that would be, say, hydrogen bonded to carbon by some means. Okay, so here we have 2 electrons in that bond. And those 2 electrons are being shared with carbon and with hydrogen. And those 2 count for the duet rule for hydrogen, so it's happy because it's got a bond around it, okay? And for carbon right now, the way it stands, there's only 2 electrons around carbon, okay? All right, so then we do a final check, because once we determine the number of valence electrons that we have for that molecule, that is what we got to work with. If we calculate 10 valence electrons, that's it. We have to make 10 valence electrons work. And we can't just, arbitrarily just dump in more electrons if we think we need it, or can we arbitrarily just remove any those 10 electrons as we need it? You got 10, we got to make 10 work, okay? Then once we check to make sure our valence electrons total is up to par, and we know it. And word about number 4 is when we're making structures, we keep track. We do an inventory. Every step we go, we count to make sure the octet is fulfilled and that we still have 10 valence electrons, because it's very easily, as we go this stepwise, to lose one, to lose a pair of electrons. So we keep a inventory of them as we're all the way through the point that we're actually done. Okay. Then we identify on the central atom. This is a key point. On the central atom, what are called bonding electrons and a lone pair. So bonding electrons, an example of that will be, let's take the structure of water, and we're going to show you how we come up with a structure, but we're going to eventually come up with something that looks like this, where we have 2 hydrogens bonded to oxygen in the middle. And then we're going to have 2 pairs of electrons on the oxygen, okay? Now, the lines which represent the bonds, those are bonded, okay? Those are bonded pair. These are being bonded between the oxygen and the hydrogen. And there are 2 in this example, because oxygen is a central atom. We just care about what's in the central atom. There are 2 bonded pair. I'm just going to call them BP, bonded pair. Now, the lone pair are the ones that are on the central atom, but are not bonded. And hence we call them lone pair or unbonded. You may hear that term. And so you can see for this structure of water, there are 2 lone pair LP on the oxygen. Again, we only care about the central atom. So this structure of water has 2 bonded pair and 2 lone pair. Remember, pair means 2 electrons. So if you count the number of electrons around oxygen, we have 8. Okay, remember that line that we draw? That is the same thing as saying 2 dots, okay? that line represents equal. I want to put equal, but I don't want to confuse that with the double bond. So a line versus two dots is one or the same. Okay, so if you count the number of electrons in that line, there's a total of 4 electrons that are bonded. There's a total of 4 electrons that are not bonded. They're lone pair. So around oxygen, there are 8 electrons. The ones bonded with hydrogen are being shared with hydrogen and oxygen. And there are 2 in that bonded pair. So therefore, hydrogen is happy. Remember, hydrogen has a duet. Its rule is a duet. Everybody else has a octet that needs to be fulfilled. Now, given the number of valence electrons that we have to work with, once we put the preliminary structure together and everything is bonded, and we count our valence electrons, if the octet is not fulfilled, then we start creating, with the valence electrons that we have, double bonds and triple bonds. Okay, and we're going to use some examples of that. For example, this structure here is a hydrogen single bonded to carbon, triple bonded to a nitrogen, and then a lone pair on the nitrogen. And we're going to use this example how we had to create triple bonds between the carbon and the hydrogen. We have a total of 2, 4, 6, 8, 10 valence electrons. I short name it VE, valence electrons, total 10. And when we go through this example, we're going to see that the octet's not fulfilled on one atom or the other. And therefore, we need to start creating double bonds and go all the way up to triple bonds until such time that we have the octet around all the atoms and the duet around hydrogen. We talked about hydrogen. There's a single bond with hydrogen and carbon. That's 2 electrons. Hydrogen's happy. If you look at the carbon itself and count the number of electrons around it, you will find 8. Okay, 1 triple bond and 1 single bond. And if you look at nitrogen all by itself, you will find a total of 8. We got a triple bond that is shared with a carbon, and then we get a lone pair on nitrogen. Okay, that's a total of 8 electrons. So the octet is fulfilled for nitrogen and for carbon, and the duet is fulfilled for hydrogen. Okay. All right, so let's take an example of this. Let's take water. Okay. So water, first thing we do, you're given the formula H2O. And, by default, you might just remember this. Hydrogen, oxygen in water is the central atom. Okay. All right. So we have 2 hydrogens and 1 oxygen. Okay. And so if we go and look at the periodic table and find out where hydrogen is, you'll find it to be in the first column, 1A. That tells you that there is 1 valence electron for each hydrogen. And so it has 2 valence electrons that come. Hold on, I'm getting. Up 1 second. Go back to my. All right. Okay, so we're doing H2O water. And so there are 2 hydrogens, okay? And hydrogen is in group 1. That tells you there's 1 valence electron per hydrogen. And since there's 2 of them, we get a total of 2 VEs, valence electrons, okay? Oxygen, there's only 1 oxygen. And oxygen is in group 6, group 6 of the periodic table. We don't have to memorize it, just find its position and find its group. That tells you that there are 6 valence electrons around oxygen that oxygen brings to the table. So we have a total of 8 valence electrons, okay? And that is the number we need to work with. We can't take out one, we can't add anymore. That's it. Because hydrogen, there's 2 hydrogens, each one brings 1. There's 1 oxygen, which brings 6. So we have a total of 8 valence electrons. Now what we do is we divide that by 2, and on one note, we're always going to end up with a number that's divisible by 2. Now why do I want to do that? Because that tells me now I got 4 pair of valence electrons. And now I can just do lines, because remember, a line, it represents 2 electrons. So when I draw something, I can do either draw a line. It's just easier to keep track of pairs than it is to keep track of single valence electrons, because you can have an example where you got 32 valence electrons to work with. Well, you can deal with 32 valence electrons. That's a lot of dots. Or you can divide that by 2 and you got 16 pair to work if you just draw a line. All right, so our magic number is this: 4 pair, or a total of 8 valence electrons. That is what we got to work with. No more, no less. Okay. Now, oxygen is the central atom. So the first step would be is to write the central atom. Put it down there. Okay. And then at that point is to see what is bonded to the central atom. Well, we got an H2, which tells you that there are 2 hydrogens bonded to the central atom. Well, I can very quickly draw a line and add a hydrogen like that. Okay, that takes care of one hydrogen. Then I put a second one. Now that took care of 2 hydrogens, and guess what? It took care of 2 pair. So from the 4 pair that I have to work with, I can subtract 2. I got 2 pairs left to work with. I got to put them someplace, okay? Obviously, I cannot put them on hydrogen. Why is that? Because hydrogen is happy now, if you will. It's a duet around hydrogen. It's got a bond with the oxygen with 2 electrons. And those 2 electrons are being shared with the oxygen and the hydrogen. So they count toward both the singly toward the hydrogen or the oxygen, as we're counting them because they're shared. So the only place to put those 2 pair right here has to be on the central atom. And so what I'm going to do is just put them on there. I'm just going to draw a line. There's 1, there's 2. That took care of my other 2 pairs. I got 0. Okay, pair to work with. Now I go back and double check. I should have 4 pair around all together, because I started off with 4 pair. And sure enough, I got 4 pair. Okay, 2 of them are bonded to the hydrogens, and 2 of them are sitting on top of the oxygen. Okay, and so we have 8 pair. We're good. Okay, structurally, that's what it is. That's how our electrons are. Now, how do we know the geometry? Well, this is where the general formula of A, B, X, and E come into play. Remember that from the Chase table? Okay. H2O tells me A is always 1. And that is a central atom, and that happens to represent oxygen. B is how many atoms are bonded to the central atom, and that number, that subscript is 2, because there's 2 hydrogens. B can be they can be the same atoms or they can be different. We don't care what they are. We just care how many of whatever is bonded to the central atom. We have 2 of them. They just happen to be the same, and that's hydrogen. So A, B, 2. Now we look for E. E is only for the central atom, because you can have lone pairs on the other atoms, but we don't care about those. We only care about what's in the central atom. So on the central atom, sure enough, we got 2 lone pairs. So E becomes E2. So our general formula our general formula. Okay, I can't emphasize the point. That's our general formula. That's not the formula for water. The formula for water is H2O, but the general formula for water is A, B subscript 2, E subscript 2, which tells you there's two moieties bonded around the central atom and two lone pairs of electrons. With that information, you then go to your shapes table and look for AB2E2. And here we go. So we start off in the first column with the general formula right there. And we got AB2, AB3, AB4, AB2E, okay, AB3E, AB2E2. There it is. Let me move it down a little bit. And for water, it is given from the general formula. I now know the geometry. Here's the structure here, where I have, this would be oxygen in the center. This would be hydrogens being bonded. And then here's the two lone pair. That geometry has a name that we call bent, okay? And then we have its bond angle between the two hydrogens is 109.5. Now here's something to remember to put in long-term memory. Whenever you have a lone pair on the central atom, automatically think polar molecule. Okay, polar. Polar means its properties are very water-like. Water, we use water and oil as our reference point. Water is extremely polar, okay? And oil is extremely non-polar. And to remember, like dissolves like, which means that polar material will dissolve in polar solvents, okay? Uh-oh, I cut out. Uh-oh. In and out, in, oh my goodness gracious. Yes. Can you hear me? I'm looking up at my connection up here. It went green again. Okay. All right. Okay, so let me repeat that. About the polarity, maybe? Is that where I got cut off? Or let me just start it from where? Let me just start it from that general formula, okay? And so that general formula was AB2E2, which gives us the geometry here in the second column, and that's what it looks like three-dimensionally. We got the lone pair sitting there, and it's got that little shape. That's just to kind of show you that that is like an orbital, if you will, where those two electrons occupy, okay? There's two of them on the central atom. And what I was saying is whenever you come up with a geometry and you end up with a lone pair on the central atom, you can automatically think with respect to polarity of that molecule that it is polar. You don't have to go any further. And we'll explain why that's the case here in a bit. So, and what we mean by polar, we're using water and oil as our reference point. Water is very polar. Oil, as we know, is non-polar. Now, we all know like dissolves like, right? Because if it didn't, you know, oil and water do not mix. Don't believe me? Get some Italian dressing. Okay, you got two layers. Look at pictures of oil spills. You got a big mess. Okay, different types of polarity. And so when we have lone pairs on the central atom, you can 99.9% of the time say it is polar. It will be polar, but more on that later on. Okay, so now why?
Professor, I have a question.
Yeah, go ahead.
So you're saying that when you have a long pair, that means that you're going to have a non-polar molecular.
No,
No,
no. What I said, oh, I'm getting feedback.
feedback.
Yeah, you might want to
want to.
block. I mean, there you go. Thank you. Now, what I said is when you have, let me do a different color here so we can distinguish. When you end up in the central atom with lone pair, like that one, and this one has two of them, okay? And that's your general formula you come up with your molecule. You can 99.9% of the time say you're going to end up with a polar molecule, not a nonpolar, polar, when you have lone pair of electrons, okay? That's what I said. Nothing to do with nonpolar. And that's just a little guideline because down the road, you're going to be looking at the bonds. And when we talk about polar bonds and determine whether the molecule is polar or nonpolar, okay? Because then that tells you what type of properties it has. But before you even have to go to the bonds, whenever you end up with lone pair, like we just did, you can say pretty quick and efficient and 99.9% that you got a polar molecule. There is a difference now, okay? There's a difference between polar bonds versus the molecule. The bonds is what's going on within the molecule, and they have an effect on the overall polarity, okay? Overall polarity. So you can have polar bonds and a nonpolar molecule. But we'll get to that here in a bit. I just threw that out here for you to kind of give you a heads up. And so from the general formula, we end up with a geometry to give you an idea what we're looking at three-dimensionally, okay? And that geometry that you have gives you the shape and then gives you the particular bonds involved. The bond angle happens to do with whatever's bonded to the central atom, how they are relative to each other. Now, one of the most common kind of a reference point is the AB4. We call that tetrahedral. Okay, you can see here that there's a central atom, whatever that may be, and then there's 4 species bonded around the central atom. Obviously, we have, connection going stable again. I freeze up and I'm going back. Okay, you know what I'm going to do when we take a break? I'm going to move over to my hotspot on my cell phone. Maybe they'll minimize this cutting out and cutting in. So maybe in about 2 o'clock is when we take a short break. I will shut down, if you will, and then boot up again using my hotspot on my cell phone. Okay. All right. So I'll say that I'll cut out again. All right, let's do that now. Okay, because I don't want to cut out too much for you guys. Let me stop the share real quick. My apologies for my connection. What I'm going to do is this. I'm going to shut her down. I'm going to start again using my hotspot because it's definitely a lot more stable than Cox.